All right, so we are going to go over the least squares regression line. Now, this is a big deal, so pay attention because you're going to be dealing with this a lot, and it's pretty cool. It's a pretty cool concept. So what we're going to do to, get our understanding down of this least squares regression lines, we're going to work with this data here where we got some basketball players with their time played in minutes versus their total points scored during the season. And we're going to look at a scatter plot of this data already made for you here. Now, if you remember like back, maybe even in like middle school, you had scatter plots and, you were probably told something like, make a line of best fit for your data. Meaning just like make a line that you think best fits it. You make a line that you don't think goes through the points as best as you can. That's what we're going to do first. We're going to come up with our own equation for a line we think best fits the data. So let's say I have this, maybe like over here. I'm probably not going to want to do something like that or like this. I'm probably going to want to do something maybe like this. I'm going to pick the line that one of my students had picked before in this class. Here's his line. The line that one of my students picked in pink. And the equation that we have for this line actually is y hat is about 0.386x. Going through the origin and going through there, it's about a 1350. Anyways, so that's our line of best fit. But now it's like, well, like, what if you don't like make a line that's exactly like this? What if what if someone else in the class is like, no, I'm not really down for that. I don't really think that line's good. I think I got a better one. They're like, I'm gonna make my line, it's purple. Distinguisher, like, yeah, I think my line is better than this one. I think this one, whoa. Bump in the road there. I think this purple line here is better than that pink line. It's like, you have two students arguing, and, we actually figured out what the equation for that pink and purple line were. We found that this one was 0.486x. Now these are lines that my students have actually picked previous years that I've taught this class. And question is, which one is better? How do you know which one is better? Like, are we just gonna look at it and say, oh, the pink one's better because I think it's better. Purple one's better because I think it's better. Like, that's not gonna be okay. We can't just use our opinion and saying this is in history or English classes, math class. We gotta be a little objective about it. We gotta figure out a way to prove in like a mathematical number or something, formula that can show my line is better than the other line or whatnot. So here's an idea. What we can do is figure out how close each line is to all the points. So for the pink line, these points, I'm going to draw vertical line segments, like this. And, over here we get a little farther. Here we got crooked, but fix it. So here, like these vertical line segments basically kind of show me how far the pink line is. So now let's look at the purple line. Purple line, let's draw vertical line segments from the points of the purple line. They're a little close to these ones over here. But again, as we go over here, we have, it comes farther and farther from these points, but then it's closer to these points than the pink line. So the purple line is closer to the points over here, but farther than the points over here, and vice versa for the pink line. So we have to be like a little more specific. How far are they from the lines? So what we can do is to calculate these distances these distances are actually known as the residuals. So what you can do is calculate the actual distances that all of those lines are from, or for that all of those points are from their line, and measure and you know, measure them again and add them all up, you know. So let me actually show you what we did in the we have all this data. We found the residuals of these values. So going back, cover this last column, but I don't want to give it away. But here in this table, what we did is we took the data from the, you know, the scatter plot, the minutes played, points scored. We calculated the predicted values based on their based on the equation, and then from there we calculated the residuals. Now let me actually show you how you can do it in your calculator really quick. All right, so using my calculator, remember I could go into my lists, edit, and list 1 I put the time played, and in list 2 I put the minutes, or sorry, the points scored. And what I can do is in list 3, if I highlight the actual list 3, I can calculate the predicted y values in here by simply writing the equation for my, you know, y hat. In this case, it's 0.386. Whoops, not 0.386 x, but x is list 1. So what I'm going to do is type list 1, 0.386 L1. L1 is, you know, this key right here. Press enter, and bang, so my list is already completed. So all these values here. Now in list 4, I can actually find the residuals by highlighting list 4. Remember, the residuals are the actual y values, which is in list 2, minus the predicted, which I just created. So it'll be L2 minus L3. L2 minus L3. And I'll get my residuals in list 4. And so I can do that to find my residuals in list 4. And I can, and that same thing for the equation of my other line, which I did down here. So I did both of my equations. And let's go back to our, you know, drawing here that we're comparing. So we're basically trying to compare the lines to see which one has a smaller sum of residuals, because we can add those residuals, and the one that has a smaller sum means it's overall less far from the line than the other one. However, if you look at these residuals I have in list 4, you see how some residuals could be negative. We already know that because some points could be below the line. So the problem is that when you have negative residuals and positive residuals, they can cancel out, meaning that theoretically you can get a sum of 0. And if you have a sum of 0, you're basically saying, oh, your line is perfect. But you know it's not perfect because obviously it's, you know, not on the line. But yeah, they're only 0 because some are negative, some are positive, and now you have this whole issue with adding up these residuals, because it's not gonna now solve your problem of which line is better. So we gotta do something. You gotta do something else. You gotta figure out another thing. So what we do is create a sum of squares. Well, we use the fact that we can make all of these into squares, into squared, what I call squared residuals. So the ones over here will be very small. I'm gonna do the pink one first. These ones you can't even see, these little tiny squares here. And now we get to this bigger one over here. So it's gonna be something like this. That'll be one. Another one will be over here, let's say. And this bigger one, we use a ruler to make it more, so it's more clear. It's like a full 5.5 centimeters. Not perfect square, but you know, trying to spend too much time on the artwork, but I want to get the idea. See, what I'm doing is creating these squared residuals. And this is, we're going to have some area within each of these squares. So what we can do is find the sum of the areas of these squared residuals and add them all up, because the area is always going to be positive. So we can do this for the pink line and do the same thing for the purple line. I can make squared residuals, calculate the sum of each one, and figure out which one has a smaller sum. And that'll be my winner. So like my calculator, I can just basically go and list 5, make list 5 equal to the values in list 4 squared. So I'll just make a list 4 squared, because those are squared residuals, and quickly populate it and I get my sum of squared residuals in list 5. So now I'm gonna figure out the sum of this. And again, using my calculator, I go to the stat, go to calc, one variable statistics. Let me look at the sum in list 5. I'm gonna run the statistics for list 5. So I'm gonna type L5, press enter. This is gonna give me all my basic statistics for my data in list 5. And my mean and my sum here is sigma x. My sum for the values in list 5 is a little more than 2 million, about 2 million and like what, 93,905. And I actually already wrote this, so I'm out on the table. So let me show you completely what I got for both these lists, or for both these sets of data. Here's all my data broken up and written out for my pink line. This is the pink line. The pink. And the purple line down here. Purple line, I got some squared residuals of about 1.7 million. So it does look like the pink line is worse because it's a bigger sum. The purple line only has a sum of 1.7 million, which is still less. So it still counts as a better line. So doing this will give you an objective way to measure which line is actually better and not have it simply be based on your opinion. So let's go ahead, let's write that out. For the purple line, we had a sum of squared residuals. Squared residuals was 1,724,440.440. .334. This was a sum, and for the pink line, sum we got was 2,093,905.246 about. So this one's better. This is the winner. Yay. You don't get any money, but you know, if you pick the better line, that's cool. Now, the thing is, there's even a better line. You know, the fact is that you can even do better. And this is what we call the least squares regression line. The least squares regression line. Here it is. Here's how we explain it. The least squares regression line is the line that makes a sum of squared residuals as small as possible. There's no other line that will have a smaller sum of squared residuals than the least squares regression line. That's why we call it the least squares regression line. So what would it be? You know, what would it be? How do you figure this out? Now, it is actually pretty cool. You would need actually, I think that you would need vector calculus to figure out, you would have to optimize it, blah, 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 but that's for a different class. In this course, we can use the power of our calculator to figure it out. Just go to our stat calc, go down to linear regression, go to the second one, because that's our form here. Stat calc again, press this one, a plus bx, and we're gonna type L1, comma, L2, because this means that we want to calculate the linear regression equation for the data in L1 versus L2. If you have a more advanced calculator, you could probably have just like entries where you have to input those. And we get that our equation for the least squares regression line is negative 208.73-ish plus 0.59x-ish. That'll be the equation of the least squares regression line. And then when you calculate the sum of the square residuals of this least squares regression line, we get it's only 1.5 million, which is the lowest, actually. It's about 200,000 less than our previous lines. So from here on out, when you're creating a linear model for a set of data in a scatter plot, we're gonna go and use technology to make our least squares regression line, because it's always gonna find the best one for us. Sorry guys, you won't be able to just do it by looking. And I actually made a final sketch of what it would look like, the liberty of it. And here we go. Here's what it would look like. I put in pencil. I did my best to make the squares as approximate as possible. But yeah, again, it's the same general idea, but you can see visually what's going on with the least squares regression line, and that it is going to guarantee you the smallest sum of square residuals and the best line possible.